work. So,
Не, на режим презентации.
А он переключается на одну слайд. I work with my colleagues also in the Moscow Engineering Business Institute, which is the National Research Nuclear University in FE. And I work on Moscow campus. And my scientific interests lie in the field of experimental nuclear physics, physics of detecting and measuring the ionizing radiation, how to see the invisible. Okay, proceed. Introduction. And mostly in the fields of development of new radiation technologies, different detector types for measuring radiations, including fundamental areas of physics, for example, neutrino physics. In our lab, we constructed a large, quite big neutrino detector. We exposed it at the nuclear power plant in Russia. And as I noticed, passing through the whole in this physics department, that your university has a nice history of conducting experiments in the fields of studying cosmic rays in the high mountains, and that the first high mass was detected in the cosmic rays here in Bolivia. That's very nice experiments, and I don't know the background of the public here. Some people from different parts of Bolivia that were listening to us online. Some people, staff members, and they have solid backgrounds, and some people are newcomers, and I think my slides will be okay for everyone who's here. Yes. Frankly speaking, my colleagues did the lion's share of my work. They really gave a lot of information about the subject, and our lectures may intersect partly because we're focused on the same fields of physics, how to quantify and detect the ionizing radiation. So I can repeat some things in my presentation, and since we are a little bit behind the shadow, I try to finish my lecture on time. That's very important, I think. The content of my course, basically I teach with this course in math over one semester. And some graduates probably had similar courses during their education period in math. And I try to make it brief as possible to cover all aspects of radiation detection. So the content of the course was types and sources of ionizing radiation. And as we know all different types of radiation, we should know how to the ionizing radiation interact with matter in order to detect it, because that's very important. And Professor Roshan could get some details of this mechanism, and I will repeat that in my talk today. So, principles of detection, because we have different types of radiation, different particles, and they interact differently with matter. So that's why we need different detectors, and thus and do different methods to detect the radiation. That's why we have a variety of radiation detector types, different approaches how to measure the radiation. And of course, the more applied thing, I'd like to show in my lectures how we use these devices for some practical things like in everyday life or in nuclear industry. So let me start with a very short introduction to activity, and I show the slide because actually the first and a very simple device, it was used in experimental physics, was actually a film, and with type of this detector, with a photographic plate, photographic film, Henri Becquerel firstly identified the spontaneous radiation, spontaneous fission, spontaneous, and in 1903 received a Nobel Prize in physics. I want to underline that in physics sometimes great discoveries are made by devices, detectors, and people get, for example, Nobel Prizes for excellent discoveries, but in reality, behind the discovery lies the principle, the device which allows to show you and detect some particles which lead to Nobel Prize. That actually happened, and with Becquerel, he tried to study X-rays with uranic cells, and thought that X-rays can lead to some sort of X-rays if you expose some material to the sun. But accidentally, when we had wet weather, some days were not sunny, and he put his uranic cell on the drawer and identified after a couple of days that there is a sign of the so-called Maltese cross. Actually, some people call it was keys, some people call it was Maltese cross, but has some a picture of this device, this subject, actually left a clearly visible shadow on the plate. It was a first detection of radiation. So, but people started to move forward technologies, and for example, in the beginning of the 19th century, Charles Wilson invented glass, which is called Wilson chamber, cloud chamber, and you can see some pictures. They can show a trace or interaction of particles with supersaturated water vapor, which leaves a trace in the detector. And in the corridor, I noticed nice pictures of chemisins for detected in the mountains. So similar pictures. It's very nice. Then people started moving forward and came up with an idea of the detector, which is called bubble chamber. The principle is simple. It has a superheated liquid, for example, liquid xenon is used, and boiling of these superheated liquids is detected. They can have quite big sizes. These detectors, here you see the picture of this detector in scientific center, I think, in CERN in Switzerland. And here I underline that sometimes the Nobel Prize goes to the physicists who conduct the experiment, but sometimes the scientific society understands the importance of the device, the detector itself, and gave the Nobel Prize to Thomas Glaser, for example, for invention of this bubble chamber and Charles invention of the bubble chamber. So, and now, of course, we don't use now this kinds of detectors for some reasons, because the first reason is that you come back to the photographic films, you can get the radiation, but you can't quantify radiation. You can't get, for example, the energy spike, and you can't process a lot of information, great amounts of data, and record them properly. So that's why now we have a great number of other technologies which we use in modern experiments, modern applications. And in this course, I will go, I guess, the majority of them. So, why there are so many variations of detector design? In principle, because actually no single device can detect all sorts of radiation, and we sometimes need a combination of detectors to detect the ionizing radiation. And sometimes there are different tasks. You know, for example, in some experiments, you need to measure flux particles, energy. In some experiments, you have to just know the type of radiation. So there are some experiments that, particularly in the fundamental physics, where we should know the position of the interaction, charge, mass ratio, and velocity, for example. And here we can see application of radiation detectors in different fields of nuclear technologies, studying radiation monitoring, dosimetry, where we have a course, spectroscopy, nuclear instrumentation and control, waste management, common security, of course, nuclear medicine, geophysics, material science, of course, fundamental aspects. So, understanding the origin of the universe and where we have massive experiments where detectors can achieve sizes over a billion, something like big settings. So just I repeat a little bit on this ionizing radiation. Actually, it's a flow of energy which is in the form of particles, which can travel through the matter and detach electrons from the atoms. It is causing the atoms to become charged, rarely ionized. We call it ionization process. Frankly speaking, it's just you detach all electrons from the atom, and you have an ion, which is a positive charge, and an electron, which is negatively charged. It's a combination of this system. And here is a matrix of all particles, a simple matrix particle. And we can divide all ionizing radiation into types. So charged radiation and uncharged radiation. Actually, charged particles, as my colleagues have mentioned, they directly ionize the matter. And uncharged particles like neutrons or gamma rays, they create secondary particles which can ionize. It's a two-step process. And if we talk about charged radiation, there are fast electrons, or we call them light particles, and heavy particles like photons, ions, and so on. So actually, all particles except of electrons and positrons, which the positive electron, if we call it, are actually heavy particles. They interact like heavy charge particles. The traditional unit of energy is electron volt, and electron volt is equal to 1.6 times 10 to minus 19 joules. And usually, as we work with cycles, we upgrade with kilo electron volts, so mega electron volts. Basically, that's enough for our applications. In some experiments, we have GeV or energy. For example, cosmic rays, we have a much greater energy. But in our applications, it's not even more everything. So a little bit about radioactivity. We have the radioactivity law, which shows that actually already in Professor already shown this similar picture, but the only thing I would like to add that when we talk about the radioactive decay, we should keep in mind that we have not a single nuclei. We have an ensemble, a great number of nuclides which can decay. And if we look at this number of nuclides after some period of time, we can see if we have a radioactive element, we can see that the number of these elements is decreasing, and the number of these nuclide is decreased and is governed by the exponential law. And here we can see this simple question. Actually, the exponential law dictates a lot of processes which happen in physics, especially in particle physics. And here we will have T parameter, which can be explained as a decay time. If you have E here, or if you have amplitude here, you will get T, which is a half-life, rather than 5. And I just wanted to show that in order to significantly decrease the activity of the element, you have to go further to several half-life periods because it's exponentially. Yeah. For example, you can see up to 10 periods. You can see that number of lamps running applies as well. 1,000. If you have 100 at the beginning, it's very important. Like we talk about the activity and try to understand if can do some period of time or not. Have some basic implant transitions. Alpha decay, beta decay, gamma decay, transition like capture. I think Dr. Losh for details, but please say that. Let's keep the slide and let's move to the next slide. And here, I just want to talk about radioactive sources. In order to work with radiation detectors, we have some instruments to calibrate them to show the response of the detector when you respond to some radioactive source. We have calibration sources in the left, like white compact, and they have some different properties. And let me here you can see some pictures of very simple radioactive sources, which is called Ph.D. type sources in Russian. That's small source that's about 2 centimeters wide, and we have this structure, and the radioactive material actually is located inside. And the diameter of this spot with radioactive material is about 3 millimeters. So the main danger is located here, and we call these sources like point-like sources because of their size of radioactive material is very small compared to the size of the detector. It's located at some distance and the size of the source itself. Usually these radioactive sources are not very intense because we usually use that for example sometimes it depends on the vertical work in our lab or for some calibrations. But if you want to have more intense sense, first you can get them, but they're more complicated. And then back to the method of containers and we apply like this. It depends on the radioactive material which is located inside. It depends on the intensity and so on. And here, I'd like to show and remind you that what is the energy spectrum. When we talk about radiation sources, we need to know the energy spectrum of these sources because there are 2 types of energy spectrum: the continuous one, which you can see here, and the non-energetic spectrum or discrete spectrum. Just an example, actually, it should be a delta function with ideal case. And the main difference that also you have an ensemble of radioactive elements that decay. And if you, for example, one decay on this plot, you will get this energy. If you have a second decay and the plot on the and then on this graph, on the second point, and if you have, for example, 1 million events, you can plot them in this graph and combine all these dots and get the incident spectrum. If you talk about the discrete spectrum, you have all dots that are concentrated in one place, in one energy, and you have this picture. Why? Well, why it's important? Because if you want to get a response to the detector and know the response in some area, you have to understand the response of the detector, the exact energy. That's very important. So some examples, I will here pass through all radiative sources which we usually utilize in our lab. For example, start with decay. We have current isotope, in the case of dot isotope, and we have also 2 particles with an electron and electrons and tritium. This reaction is called a 3-body decay. You have 1 parent isotope, which actually decays 3 particles. And this reaction is very prominent because actually when physicists started to do research on beta decay, they expected to have a 2-body decay spectrum, which is actually a monoenergetic spectrum. But it occurred that in real life we have a 3-body spectrum, and it was postulated that there should be 1 more particle, and physicists called it neutrino, and this particle actually explains the nature of the spectrum. So this energy spectrum is continuous energy spectrum, and most common isotopes that we use, especially Bronson 90, is used in the lab for studying the response of electrons. If you need, sometimes you need a monoenergetic spectrum, and here we can get electrons of internal conversion, or we call them conversion electrons. And this happens when you have a stable nucleus, which is excited, and some of this energy can go directly to 1 of the electrons in the orbit, and then it is transferred to this electron. Actually, we have a picture like this with conversion electrons. The main disadvantage is also that the energy of these conversion electrons is not leaking out, and that's in reality the only source of electrons with energy, really energized. Here, because the isotope is okay, and most common isotope, for example, carbon 109. And the third way to get discrete energy spectrum of electrons using Auger electrons, but the energy basically lies in the very low part of the spectrum, and this process frequently happens in isotope with low Z elements, the same isotopes. Here the picture happens. And we covered all electron sources. Now we are moving to heavy charge particle sources. Actually, the first reaction where we can get particle out decay, and compared to an electron, beta decay is a big difference between beta decay, alpha decay, as alpha decay is a two-body decay. You can see we don't have an extra particle, the further extra particle here, and we have the reaction like this, and we have a nuclei, which is actually half particle. Alpha particle is pretty heavy, both compared to the electron, and the spectrum is more energetic. It's a two-body decay, and alpha particle energy is for the majority of radioisotopes of light range of 46 megavolts. Half-life these isotopes can be several hundred years, and with some tendency that half-life currently lies anti-correlated with energy of alpha particles. Electric charge of particles +2, and most common isotopes are using 241 and plutonium 239. So mostly used different sources. And the second reaction where we can get heavily charged particles in spontaneous helium, where some elements we have number of elements can decay in fission fragments and produce heavy charged particles. Yeah. Some nuclei are splitting into two smaller nuclei like this, and for example, and the alpha particle also, and the common source of this spontaneous helium is californium-252 isotope, which is actually produced only in two places in the room. And talking about gamma rays, also very important, and there are 6 ways, approximately 6 ways to create gamma radiation sources in the lab. And the first one is called gamma rays, which are formed by beta decay, where you have isotope, where you have beta decay, and you have a transition. For example, here for cobalt, since the isotope, you have 2 gamma rays where energy is about 1 MeV. And the spectrum, of course, is more energetic because you have an excited state when a gamma ray is emitted, you always have a more energetic spectrum. Conventional sources, which are used as in lab or in some practical applications, season 157, 16, 7, variable 1, 1, up to 15 isotopes used. That's what I will plan. And the second way of getting gamma rays is through annihilation radiation, and you have an electron and positron which meet each other, and they produce 2 gamma rays with energies of 4.5 MeV, which is equal to the mass of the electron. And how this is a simple picture of how it happens. A positron and an electron, they meet each other and annihilate and create two gamma rays moving in the opposite direction. So, sources: sodium 22, copper 64. Sometimes we can have gamma rays using nuclear reactions. For example, have a reaction with a really light element and bombarded with an alpha particle, will get excited state of carbon-12 is neutron. This is actually a reaction where neutron is detected. Here you can see you have some decay, and you can produce gamma rays with energies up to 10 MeV, I think, in some reactions. The next one is the German word Bremsstrahlung, this, which means the acceleration radiation. And here fast electrons interact with matter and produce a spectrum, a continuous spectrum of gamma rays. The fifth reactions with X-rays. We have X-rays when we have some, for example, some preliminary interaction of a vacancy. Some electron is needed, and this vacancy can be filled with another electron, which is orbiting one of the nuclei, and then this process happens. The abundance of energy is immediately in the form of X-ray with a discrete energy. And we have a picture like this. For example, this is a spectrum of X-rays with energy, their intensity for spectrum, and we have these lines which correspond to different electron photons, for example, of beta. And the last one, which is used actually not in the lab, but you have to construct a big experimental facility to produce so-called synchrotron radiation, when a beam of energetic electron is orbiting, but actually it's a particle accelerator, and it's orbiting inside at you, and if it changes its trajectory, it emits some light in the form of synchrotron radiation. This is one of the most sophisticated sources of photons to study, for example, molecules, something like this. Here we are covering the last type of sources, starting with Newton. I hope that some of you know that Newton actually consists of three smaller particles, just called quarks. For example, Newton consists of U and two Z. Oops, just a reminder. Oh, forgot. And Newton was discovered by J.F. Chadwick in 1932. And just one fact, that the mass of Newton is a little bit bigger than the mass of proton. That's why we have that Newton decay reaction. Some properties of Newton, not of them are important. First, I think most important that the electric charge is equal to 0. And the lifetime of Newton, of course, Newton is stable, it is located when is located inside the nucleus. But then it's not inside the nucleus, it's free, tends to decay, and the lifetime approximately is equal to 900 seconds. And here you have to understand also that it's not the life of one neutron. We also have an ensemble of neutrons and measure the average life of the life. We have the same exponential decay and measure the parameter tau, which is located in this exponent. Very similar to simple radiation decay. That's almost the same, but for neutrons. So neutrons are very important, but with one difference between neutrons compared to gamma rays, for example, because as I said, there are gamma sources which have a preliminary better decay. We have an excitation state. Fortunately, there are no such type of isotopes with neutrons. Only one with brom 5, but the lifetime of this isotope is very short, less 1 minute. And that is why we have conventional lab sources for neutrons, which are spontaneous fission and nuclear reactions. Spontaneous fission, the same thing, that's for heavy charge particles. That's the only difference, that also in addition to alpha particles, heavy charge particles, we also can have neutron and have some on average we have some spontaneous neutron yield, which you can see here. The main problem that's conforming to very precious materials, and the cost of production of this size isotope is very high. The second one, same reaction, about beta and direction, then we can have get some reactions also, which are called photoneutron reactions, have quite energetic gamma ray heated with to the, for example, beryllium isotope, and we will also have the neutron. The main disadvantage of this reaction is that you have a very intense source of gamma, because the ratio of gamma to neutrons is not so high, and you also have a large gamma rays background. And the last one, source of neutrons, which is very important, and actually we have special devices which are called neutron generators. Where we can produce high energy neutrons, monoenergetic high energy neutrons. Here we can see some thermonuclear reactions. For example, you have deuterium isotope heated with deuterium isotope and get helium-32 and the neutron. The same thing as with deuterium-tritium reaction. The difference when we have helium-4, that's why we have different energies of these reactions and have different energies of neutrons. For example, with PV reaction, and energy was produced about 14 MeV, or 3 MeV, sorry, and 14 MeV for the T reactions. The main advantage of this device is actually it's a compact accelerator, and we can get, as it's accelerator, we can get a high intensity neutron fluxes, and they are can grow in pulse mode, have some like some source of neutrons, which is similar to, for example, protons in accelerator beam. There are some other isotopes which we can exploit also, but for example, beryllium or lithium-7 is very promising, but we need higher energy, so we have particle instead particle. Here the picture how it looks like. That's the possible device. You have an ion source of hydrogen plus 2. Yeah, we have high electric field up to 300 kilovolts in order to accelerate hydrogen ions, and they target where it produces neutrons. So here the same picture, very similar to what we have already showed. Different types of decay, different alpha, beta, gamma, and neutron, and they interact with different materials, different. And why it happens so? Because actually it's naturally lies in nature, because we have different interaction mechanisms, different particles. Alpha particles more intensely lose their energy from interactions with the material. Beta particles deposit less energy, and gamma rays have 3 processes to interact with matter. That is why it's somehow more complicated to stop the radiation. And neutrons, the way of neutrons interacts with matter strongly depends on the neutron energy, firstly because the probability of the interaction, the cross section depends on the energy incident neutron. And the best materials, of course, some know to stop the radiation. If we talk about lead, if we talk about gamma rays, it's lead, more light materials, and store alphas and betas, and water elements with light elements like water, for example. There are a lot of hydrogen atoms can stop neutrons efficiently. And why it happens in this matter actually lies in the nature of interaction of particles with matter. Just I can ask you as well, coming to the end of our lectures, according to the schedule, and just ask if you're tired, I can stop now, take your questions if you have, and proceed with the material tomorrow. Good. depends on you, or I can give, for example, some details about how different type of radiation interacts with methods.
Well, actually, this we have a shift in lecture because we spent some half an hour at the beginning of lecture. So actually, the duration of lectures was supposed to be 1.5 hours. But before this,
Okay, great. I will continue with, I think, some slides to show you the nature of interactions, at least of charged particles. We start with heavy charged particles, and heavy charged particles, as you already know, all particles except electrons and positrons, they interact primarily through the Coulomb force, because charged particle has an electric charge, and the atom has electrons, is located in the atom. And simply speaking, when the charged particle moves close to the electron, they start feeling each other, and during this process, some interaction happens, and particles, the incident particle, incoming particle, transfers some energy to the electrons. The main difference is lies in the mass of heavy particles and light particles. Heavy particles is almost boson, for example, is at least 2,000 times heavier than an electron. That is why during one interaction, alpha particle can transfer to an electron much less energy in the interaction. For example, if we look at take an example now, the particle with energy 5 MeV can transit about 2.7 keV to the electron, and it requires about 500 interaction energy. And the electron, the opposite, has a small mass, which is comparable to the mass of an electron, which is orbiting the atom. And during one interaction, the electron will give much larger fraction of its energy to the electron. So in one encounter. Sometimes also, as the end masses are comparable, we have some deflections and have different angles of vectors. So that's why we have the picture like this. This stands for heavy, this stands for light. Basically, heavy particles have shorter tracks in the material, and they look like a straight line. And electrons, positrons, they have some trajectory with, for example, several different directions, more complicated trajectory compared to heavy particles. It's long. Here, picture is of ions and electrons interact with matter. This also one thing I'd like to say, that not only the primary particles, for example, electrons or ions can ionize the matter, but some of electrons which were detached in the original atom can get the energy. These electrons called are secondary electrons or delta electrons. These electrons have enough energy also to ionize, and this ionizing radiation is called the first particle incoming particle is called the primary ionization, and the second one is the secondary ionization. And that's delta electrons. Here we start with this quite complicated formula, which is a Parte block question. Just it was derived actually theoretically that any charged particle, specifically this question is specifically for heavy charged particles, should obey this equation. And the problem actually here comes the definition, which is called the stopping power, and sometimes we call it deep G's. They actually that's an energy which is lost during the interaction along the track of the particle. Here we put the minus sign, just showing that there's always a decrease of energy. And this quite complicated formula, and I would like to show you only a couple of parameters here which actually matter. Atomic mass of solver here, and atomic number of incident particles here, and atomic here, and atomic number of the solvent. What it shows? It shows that if you have larger electric charge, this particle loses its energy more effectively in the material. And that's extensible Z number, and atomic number of absorber also matters, because when it's high, and the V predicts is high as well. Just some parameters for these cases. I'm not going to dig into details. And some rules about this block formula that we have this picture, which is basically standard picture which shows me when we talk about stopping power. The ionization losses, they are decreasing in some energy range, then achieve the minimum, and then go upwards in some energy range. And this minimum usually is located somewhere between 1, 2, 4, 5 EV within expressions rounded there, and then what unit the X, because we measure energy need and mass, and X in centimeters, which is also takes into account the density of the material. That's why we have this formula. And this minimum responds to the so-called minimum ionizing particle. And for example, cosmic mutants particles passing to us, and we have the X about 2. And this minimum very similar to many materials. And one more thing I'd like to mention, so-called breadth curve. I think my colleagues will give more details about this picture, which shows that the heavy particle loses more energy at the end of its track. And we have a peak, a massive peak here, which actually is very important for proton therapy in the limits. One more thing that actually as all particles and the process, that's the stochastic process, and the number of interactions is different for different, for example, we have a great number of alpha particles. They actually interact a little bit differently and deposit in the detector different amount of energy. It differs slightly because the nature of ionized radiation is stochastic. That's why we have so-called range triangle, that we have this picture where we can define actually the range of the particle, the mean range that defines that we have a source of the detector, the absorber fixing thickness that produces the counts of particles to exactly 1/2 of its value. But the mean thing you can see here is approximately half of its intensity. The same thing is applicable for electrons, compatible formula, I mean, but looks a little bit differently mostly from theoretical point of view, because the electron is lighter. Some equations were used to deduce this formula. But the main difference between heavy particles and light particles, that the second factor plays an important role in this interaction, because we have the Bremsstrahlung, and the Bremsstrahlung is a factor of the particle mass. The intensity of Bremsstrahlung is inversely proportional to the mass of the particle, and when we have quite significant energy, for example, in a V region, electrons can ionize the material and also at the same time produce the Bremsstrahlung radiation. And in order, if you want to calculate all the energy loss in the material, you have to summarize the two things. The first one, which is attributed to so-called collisional losses, which is losses of energy which are associated with the ionization, and excitation, lies in beta block formula. And the second additive is all energy lost by Bremsstrahlung, because finally you have a finite amount of materials to absorb the radiation. All Bremsstrahlung also would go to the ionization parts sometime, and in total we have these factors. And also here comes at the ratio between radiation and collisional losses. described by this formula, and here you can see E, which is an energy, which is called the critical energy, and critical energy just shows you a threshold energy when the additional losses are equal to radioactive losses, which are actually the branch flow. If we move forward, I think I will discuss also I covered all interactions of charged particles, how electrons interact with the formula, and light particles, heavy particles, and now we come to uncharged particles. And here some difference between the interaction of gamma rays with matter compared to charged particles. And the main difference is that in order to detect the gamma ray, we have to convert an initial gamma ray into charged particle. And also this charged particle can interact with matter like electron, for example. And there are three major interaction mechanisms for gamma rays. The first one is photo effect. Second one is quantum scattering, and third one is reflection. And here you can see the picture, what happens, for example, atom. Here is an incident gamma ray, which interacts with atom, and as a result of this interaction, you have an emitted electron, which is called a photoelectron. And as a result of this interaction, in reality, gamma ray disappears, and the energy, the initial energy of gamma ray goes to electron, which gets this energy from the gamma ray, minus the binding energy of electron is original charge. Here, the main mechanism. The main thing that shows you how gamma rays interact with material is the probability of this interaction. Actually, this is so-called a cross-section. It is high, if the cross-section is high, the probability of interaction is high. And for gamma rays, there are two things that are really important when gamma rays interact with matter. It's an energy of gamma ray, and the second is the atomic number of the material. Because gamma ray, the energy of gamma ray is inversely a cross-section of interaction is inversely proportional to gamma ray energy according to this equation, and therefore the probability of photo effect is proportional to that to the power of 5, when z is the atomic number of material. Let's move to the third, to the second reaction. It's called quantum scattering. Yeah, simple picture. You have an electron, so actually is at rest. Yeah, it's at rest, and the gamma ray scatters of this electron, and you have a reaction where some sort of scattering, where an electron gets some energy from the gamma ray. This electron is called a recoil electron, and also you have an angle of gamma, the initial gamma ray is scattered. Some questions. This process actually was discovered and explained by the British physicist Compton, and here we can get the energy of the vacuum, which is very important for our detection of gamma rays. I will explain why in my next lectures. Also, as with photo effect, we have an equation where only you have Z without any powers, and here the inverse energy. We have a picture which looks like this, so-called quantum continuum, but I think we can keep more detail to this picture when I come to gamma rays spectroscopy in my lectures, my future lectures. And pair production, the third process which occurs when we want to detect a gamma ray at the nucleus. This process happens only we have a nucleus or some, for example, electron. We have need to the third body to make this reaction possible. And during this reaction, the energy of gamma ray goes to the energy of positron, electron, and two masses of electron, which are equal to 1.42 MeV, and that is why this is a so-called a threshold reaction, when we have a minimum amount of energy in order to make this reaction possible. And the cross-section of this pair reduction is proportional to Z squared. And we talk about energy and some question. Actually, if we talk about these processes and consider them as independent, the total cross section is the sum of these processes. We have the total cross section, which is equal to the sum of photoelectric effect, quantum scattering, and pair production. Here you can see some pictures for different material. You follow lead. You can see that in this energy region there is the dominance of photoelectric effect. In this region, the dominance of quantum effect, and this region, the dominance of pair production. And if we want to get the total cross section, we have to simply add up all of these cross sections and get the total section, which looks like this. Is the same picture on left, for example. You can see these sharp edges that associated with different cast shells and quantum scattering happening in them. And here the picture that shows different is the picture of cross-section, dependence of section of energy of gamma ray. Is the graph showing some regions where, for example, photoelectric effect dominates, elements with small energy, either Pierce Compton effect and pair production. You see that pair production is only mostly for gamma rays like the energy of several MeVs. I think it will be my last slide for today. Here's some, I would say, an application of some law that shows how gamma rays interact with matter. It's so-called linear attenuation law, and how we use it. We use it to, for example, in some applications, but one of the most, I think, important places to show how to construct a shield in order to save yourself from the gamma rays, which are very can pass through quite long materials. This is called also the same question, which works for radiative decay. It also works for shielding the gamma rays, which is called also the exponential law. You can see the initial flux of radiation, which is I zero, and then the intensity of radiation passes through the material with thickness of T. You can see that if you have more and more layers of material, you can more effectively to suppress the flux of gamma rays. And this law has one parameter, except for the thickness of material, intensities of photons or gamma rays. You have the parameter mu, which is called linear attenuation coefficients. Sometimes it's expressed in centimeters in power -1, or squared centimeters per gram -1. If we take into account the density of the materials. It also have one parameter in order to more in numbers to describe this law. We have the parameter which is called the half-wave layer, and it's the thickness of the material which can attenuate the initial flux of gamma rays and decrease its intensity in 2 times, also to get absorb 50% of all gamma radiation. This coefficient mu takes into account all these processes which can happen. You can scatter some gamma rays, you can absorb them by photoelectric or pairs, but the main thing that you have layers of materials, less gamma rays, and that's the main feature of this reaction. This is the formula that describes this, and here's some half waves of materials. For example, you can see 2 isotopes, we have 1, 2. You can see we have different materials and half-wave layers, millimeters. We see that tungsten uranium, you can see that the best stream can be made of, for example, tungsten, uranium, or lead. That is why, because the Z number is higher in these materials, and the density of materials is high. And as we have in our life, these materials are mostly used to shield gamma radiation. Here's the picture. Yeah, well, you it's not visible right now, but here it is mu, the rho, which is the density. This is the mass intonation coefficient, which is measured in this units. Here the picture showing how many layers you need in order to suppress the gamma radiation. Here you can see one layer 50%, 2 layers 25%, and 7 layers can reduce the intensity of radiation more than 100 times. That's depends on the quality of the shielding. That's a simple equation shows why I need more and more material to shield and protect yourself from gamma radiation. I think I can stop now. Tomorrow we will proceed with interaction with newtons with matter. It's more complicated, and I think I can stop now and take questions. But take your questions if you have them. Thank you for your attention. Rather questions, I can answer them tomorrow. Okay, thanks.
Thank you very much for joining us at the meeting Zoom and the participant person in the room. Thank you very much for your attendance. Well, tomorrow we will continue with this course and see you tomorrow. Thank you.